Thank you. We're going to look at rotational systems today. Okay. So today and Monday we will be looking at rotational systems, and then from Wednesday we will start Laplace transforms using all the knowledge that we've gained so far. So problem. My plan is to solve three types of problems today. Okay. Here is the first one. This is a figure that you saw from the last lecture. So I have an inertial element, that thing that is drawn as a disk, that has a moment of inertia J, or let me call it as J1, okay, just for the sake of continuity with the remaining problems we are going to solve today. Then I have a torsional spring of stiffness K suffix T. Sometimes this is K capital suffix T, small suffix T. If you see a letter T there, it indicates a torsional spring. Okay. Then I have C suffix T, the damping constant, okay, for the torsional damper. And we would like to obtain the equation of motion. So obtain equation of motion. Now, you see that there is no torque acting on the system. If you want, we can have a torque acting on the system. I'm going to do that for the remaining problems. But here is what I'm going to say, and we're going to build on this when we hit Laplace transforms. I can make a system move in two ways. Okay, so for example, here is a water bottle. Okay, I can take the water bottle and I can apply an external force on it, which will keep dragging this as time proceeds. That's one way of putting things in motion. Or I can take the same water bottle and I can apply a torque on it. Okay, I can twist this person. The other type of action that I can provide on bodies that will make them move is initial conditions. What did I do? I was here. The system is doing something, it's oscillating, and it will stop after some time, maybe, maybe not. If you just have a spring and a mass, I pluck the spring and I let it go, the mass is just going to keep oscillating back and forth forever. Okay? So those are initial conditions. So there are two ways in which you can make a system move. Initial conditions and then forcing or by applying an external torque. Okay? So in this problem, let me assume that there are initial conditions given, which means that you will not see any applied torque on the body. Does this make sense to everybody? Okay? So in that sense, I want to come up with the equations of motion, and we will make some simplifications for these kinds of problems. We will say that for rotational bodies, or rotational or torsional situations, okay, this torsional element here undergoes only a rotation. It does not undergo any translation. It undergoes only a rotation, and we are looking at two-dimensional motion, which means that there is only 1 degree of freedom if I have one torsional element. If I have two torsional elements, which is going to be the next problem, I'll have 2 degrees of freedom. So in this problem, I have only 1 degree of freedom. Okay, so we're going to say that only a rotational motion for inertial elements that are subjected to external torque. So if you want, you can think of this as being pinned at some central point or about its center of mass, and then you're just coming and giving it an applied torque of some kind. Okay? So there's only 1 degree of freedom here. So number of degrees of freedom is equal to 1 for the inertial element in torsion. And I'm going to label the degree of freedom as theta because it's a rotation, as you can obviously see. which means that we need to come up with a sense for theta. Is it what is positive, what is negative? Okay, so I'm going to call the degree of freedom as theta 1 just to build on the next problem. Okay, and I'm going to label it in the following sense. So this is theta 1 of t is the degree of freedom, and I want to now ensure all of us are on the same page. The way I have drawn this, okay, if I use the fingers of my right hand, okay, and if I curl my fingers, you see that the fingers of my right hand are pointing such that it is into the board. Does this make sense to everybody? Okay, fingers of my right hand, if I curl it, it's into the board or aligned into the inertial element, so it implies that this is a clockwise rotation that I have chosen. Okay, or if you want, you can draw a set of axes. If you are the observer standing here and you are viewing the entire situation this way, then what does this imply? This implies that it's a clockwise rotation for you. Okay, you are seeing this as the fingers of the clock rotating. If it were drawn the other way, it would be a counterclockwise rotation. Okay, so for us, clockwise is CW, shorthand, and counter CW is CCW. Okay, so from now on, this is my shorthand notation. Is everybody on the same page regarding the drawing that I have on the board? Does anybody need any explanation of what that sense is? Once again, what am I doing? I'm just setting up an arbitrary axis. The axis is pointing towards the inertial element, the way I have drawn it. Okay? And then, from the perspective of this person here, this is a clockwise rotation. Okay? Yes?
Is that kind of like an SEP?
That is not the SEP. SEP is a position where there is no deflection of the spring. Please do not conflate directions with SEP. SEP has nothing to do with directions.
So that's just the direction that it will rotate.
I do not know if it will rotate this way. What I'm saying is, I'm going to say that this is the direction of positive rotation.
Okay, great.
Okay, that was my next statement that I was planning to make. Okay, so what I'm saying is this: I never tell you that this is how the body is going to move, because I don't know. For heaven's sake, I never really know how the body is going to move. I'm telling you that if the body moves this way, this I want to be very, very clear. I have seen countless questions on this. Here is my spiel. Okay, if the body moves the way I have drawn it, what does that imply? It implies that theta is positive. If the body moves opposite to the sense that I have drawn, it implies that theta is negative. Or I obtain the equations of motion and I solve for theta and I get a positive theta, it means the body is rotating clockwise. Or if I get a negative theta, the body is rotating otherwise. Okay? Same idea as we did for the other systems. In this problem, there is no ACP. There is no ACP calculations required because the spring is not deflected due to gravity. We are not looking at vertical motion of this body at all. Okay? This body is pinned at this particular point. Don't need to worry about it. Okay? So there is no calculations required for ACP for this problem. On Monday, we will solve a problem which will require ACP calculations. So hang on to that. So ACP is done. That's the first step typically in all problems. I have situated the degree of freedom as well with a sign convention. This is the sign convention for positive theta 1 being the degree of freedom. If this is the direction of positive theta 1 dot, theta 1 double dot, they are all positive in the same sense. Okay? Makes sense to everybody? Alright. Then what we do is fairly straightforward. Okay? There is not much kinematics to these elements because I'm just looking at angular acceleration of the body, that's theta 1 double dot. Okay, so the kinematics is fairly straightforward. It's just the acceleration of the disk is theta 1 double dot. And this is angular of the element J1, and this is considered to be positive if it is clockwise. Okay? And the standard convention is to take clockwise to be positive, counterclockwise to be negative. This is counterintuitive because in statics You would have done counterclockwise to be positive, clockwise to be negative. So this positive negative business is just something in your mind. Today I can come and say something is positive this way. Tomorrow I can come and say something else is positive this way. What should not change? The physics of the problem should not change. My sign convention can change today and tomorrow and the other days. Okay? Alright. Then we do the kinetics. Okay, this is a fixed wall. Okay, so typically wall we will call as W. I draw three figures. First let's focus on the spring. Okay. I'm going to assume for a positive theta 1. Okay. What happens? Let me call this point as O. Okay, let me say that this is the point O. And this is the point W. W means it's fixed to the wall. O means it's fixed to the center of the disk. Okay, it does not matter whether it is fixed here or there. I'm not having any translational motion. I have only rotation. All right. Does this make sense to everybody so far? This is the direction of positive theta 1. And here is the argument. This side of the wall is fixed. Okay? So, to cause a rotation or a twist of theta 1 of t on this side of the spring, what should I do? I should be applying a torque. And I will apply a torque in the same sense as what that theta 1 is, because there is nothing else happening in the other side of the wall. So this is going to be Ts, which is going to be the torsional stiffness times theta 1 of t. And theta 1 of t, theta 1, they are all dependent on time. Okay, I'm not going to specifically write that out. Does this make sense to everybody? Once again, that end of the wall is fixed, so nothing special going on. This end of the spring is connected to the body, and for a positive theta 1, this end of the spring is getting twisted in the sense that is shown. So what should I do to cause a twist of that nature? I should apply a torque on the spring. And the torque that I'm applying is in the same sense as this rotation, because nothing is going on at the wall. So that's not dictating the events at all. But the figure is not done. Every body, every spring, every damper needs to be in static equilibrium, because we ignore the inertia of the spring and damping elements, which means that on the other side of the spring, I need to have an equal and opposite torque. Does this make sense to everybody? Common sense, right? Everything has to be in static equilibrium. If I choose one way on one side, it has to be the other way on the other side. No tricks, no fooling around. So this is the situation here, and I can do the same thing for the torsional element as well. Look at this. Okay, I'm going to have theta 1 dot positive in the same sense as theta 1. So if I say I'm looking at all positive rotations, then this is positive theta 1 dot. The other end of the damper is connected to the wall, so nothing special going on. This end of the damper is connected to the body that is trying to rotate it based on initial conditions or based on a torque applied. And so I'm going to have a torque here in the same sense. I'm going to call this as T suffix D. You can call this as point O if you want. And T suffix D is going to be the damping constant multiplied by the relative velocity across the ends of the damper. One end is fixed, the other end is rotating with theta 1 dot, so obviously the relative velocity is theta 1 dot. Make sense? Same idea. If you do the spring, the dampers just follow suit. You just need to change the theta 1 to theta 1 dot. That's all. Okay? No thinking required. Yeah? And obviously this has to be in equilibrium, so I have to put an equal and opposite torque right there. Alright. This is the kinetics. Just want to create some space. Now all I have to do is draw the free body diagram of the disk. Okay, on the free body diagram of the disk, here is the free body diagram. That's the point O. All I have to do is pick what's happening at the point O on the spring, pick what's happening at the point O on the damping element, and draw equal and opposite torques back on the inertial element. And now you see why they're called a restoring torque, right? For a positive theta 1, this disk fellow is trying to twist the spring in the clockwise sense. It is trying to twist the damper in the clockwise sense at the point that's connected to the inertial element. So which means back on the inertial element, the springs will prevent by producing a restoring torque in the opposite sense. So this is going to be this way. That's going to be one more there. This is Ts. This is Td. So this is equal and opposite to what I have here. Of course, these two. Okay, I just want to link them together. And link these two. Does this make sense to everybody? Equal and opposite. Okay? Like what we did for masses. I have the free body diagram of the spring. If the spring is in tension and one end is connected to the mass, it's going to try and pull the mass towards the spring. Okay? Then I draw the kinetic diagram. It's fairly straightforward. This is the FBD. Kinetic diagram. Just going to squeeze it here. This is the point O. These are all now couple moments. They're all torques, couple moments. They're all the same thing. I'm just going to draw the inertial torque, which is the moment of inertia of the disk, which is J1, multiplied by the angular acceleration theta 1 double dot in the same direction as positive theta 1. Okay? This was the direction chosen for positive theta 1, and so likewise that's happening here. This is the kinetic diagram. Alright, I want to spend maybe half a minute answering questions if there are any. This is the setup for the next problem. Okay? If you understand this, the next one is really, really trivial. Yes?
We're not going to take any free body diagrams or anything on the wall, right? Those forces are just counteracting things.
Absolutely, absolutely. So if you would like to draw the wall, what will happen is the wall will have the torques from the damping and the spring. But then the wall will exert something equal and opposite back on it, and so it's going to be in static equilibrium. But, to add on to your question, what I'm going to do in the next problem is I'm going to say, okay, hey, there is no wall, there is another inertial element connected. What do we do then? Yes, question.
So, right here, is J1 is representing what exactly again?
J1 is the mass moment of inertia, as we said in the last class. It's the mass moment of inertia about the center of mass of the disk. Okay, so. Alright, I'm going to move on. Okay, we'll answer more questions later. I'm going to sum moments about the point O on the free body diagram. This is equal to sum of moments about the point O on the kinetic diagram. Choose a sign convention, go along with what you say. Counterclockwise was chosen as positive, or clockwise was chosen as positive. So clockwise is positive, clockwise according to a person who is facing the board. Right? What are the torques? Minus Ts minus Td. If you want, if this simplifies your life, here is what you can do. I can take the free body diagram of the disk. Mark it this way. You can also do it this way. This is completely fine. Okay, if it is easier for you to envision it or visualize it. Alright, and if you do it this way, then you see the Ts and Td are both counterclockwise. J1 theta 1 double dot is clockwise, so I write it out. So minus Ts minus Td is J1 theta 1 double dot. Bring all these creatures to the right side or the left side. Combine the dependent variables together. Once again, what are the dependent variables? The degrees of freedom. What is the independent variable? Time.
Never mind.
Theta 1, theta 1.
Yeah.
Theta 1 is the dependent variable. Right. Alright, I just write it out. Is equal to 0. It's a homogeneous, linear, second order, first degree, ordinary differential equation, which will be set into motion by initial conditions. Alright? So that's the end of this problem. That's about it. These things are a piece of cake. Okay, if you understand them well, there is not much sweat to these at all. They just look scary by the figures that they don't. Another problem. We just increase the complexity by a little bit. Okay? Right, so I have a situation where I have two inertial elements now, okay? Two inertial elements. Let's call them as J1 and J2. I have a spring of stiffness K suffix T and a damping constant Ct. Now in this problem, let's say that there are some applied torques. Okay, so let's say that there is a torque T1 as a function of time. There is a torque T2 that is applied as a function of time. Once again, what are these J's? They are the mass moments of inertia about the center of masses. So this is 0.01, 0.02. Okay, I'm using J instead of I because your textbook uses J for these things, just to be consistent, okay? So that you're not caught by surprise. If you look at the textbook, they say J, I say I, so what does he really mean? All right, obtain the equations of motion. Why do I say equations of motion? Is because I have two inertial elements. If I have two elements, I'm going to have how many degrees of freedom? I'm going to have 2 degrees of freedom. Okay? What do I call them? Theta 1 of t, theta 2 of t. No thinking required at all. Absolutely no motion in the translational directions, just rotation. That's it. Okay? So SEPs, this is the first step you typically start off with. Automatically satisfied, the spring is not getting deflected by means of gravity. We're going to solve a problem where that will happen on Monday. Then degrees of freedom. Theta 1 of t, theta 2 of t. Theta 1 of t is the degree of freedom for the first inertial element. Theta 2 of t is the degree of freedom for the second. Okay? Clockwise or counterclockwise, your choice. Hang on. I'm going to choose them to be clockwise. Right, so these are the degrees of freedom. This is the sign convention that I have appropriated. It does not tell me this is how the system is moving. Please, I just want to make it very clear. I have no idea how the system moves. Okay? Neither do you, neither does anybody. How do you know when the system or how the system is going to move? Is when you solve the damn equations of motion. Until then, I have no clue. But what I'm telling you is, if indeed I have the capability to solve the equations of motion and I end up getting theta 1 to be positive, then the disk J1 is going to rotate this way. That's all I think. Okay? You have a question?
Yes, I was going to ask, so there's no translation.
That's what we have been discussing all along, yes.
Yeah.
Okay.
But like, is there any restriction to that? Like,
I mean, it's fixed axis rotation, right? So I'm putting a pin through this. All I can do is just rotate the thing.
Okay.
I cannot translate it. Yeah? All right, so I'm going to move on, perform the kinematics, which is also not a huge deal here because there is only 2 angular accelerations. Theta 1 double dot, theta 2 double dot. Okay? Then we go to the kinetics, which is where things get a little sticky. But just for this problem. If you understand it clearly for this problem, the next one is going to be easier. Let's do this. And I'll take questions once I'm completed with this problem. Okay. I'm going to keep this figure in front of us. Erase the rest of it. All right. I draw the spring. Okay. I call one end of the spring as O1, the other end as O2. This end is O2. Then I say that all my calculations are performed for positive θ1 and for positive θ2. So that if I end up with a positive answer, I'm good to go. If I end up with a negative answer eventually, it means my motion is opposite to what I assumed it to be. Okay? So for positive θ1 and positive θ2. Okay? I'm going to draw the directions for positive θ1 and θ2. Now watch this carefully. Choose any one end of the spring. Okay, if you like O1, go for O1. If you like O2, go for O2. Does not matter. Okay, I'm going to look at O1. All right. Now, θ1 of t and θ2 of t are in the same sense. Do you all agree with me? Right? They are all both clockwise. Right. So, the amount of torque that I need to apply on this end of the spring to rotate it by θ1 of t, my question is that going to be greater than or lesser than the torque I had applied here? I'm going to repeat my question. It's a lot of words. Focus on end O1, okay, all of us. Notice that θ1 and θ2 are in the same sense. The amount of torque I need to apply on this end of the spring to produce a rotation of θ1, is that going to be greater than or lesser than this quantity here? I will come back to you. I want to see some good friends of mine from the back. Any suggestions? Yes.
I think it'd be less than,
Beautiful, why?
because you'd just be rotating the entire system. If they're both going the same way and the data one equals data two, then it'd just be rotating.
Absolutely, very nice, and maybe I come back to you. Same answer, okay. Does everybody concur? And I'm going to repeat what he said. Because you're rotating θ2 and θ1 by the same amount, obviously the amount of torque to rotate this end by an amount of θ1 is going to be lesser than the amount applied here, because the system is anyway rotating in the same direction as θ1 due to θ2. Once again, because I'm rotating them by the same sense, that's important, right? Because I'm rotating them by the same sense, the amount of torque I need to apply here to rotate this end of the spring by, or twist this end of the spring by θ1 is going to be lesser than what I have here, because θ2 is anyway rotating the spring in the same sense as θ1. I'm not fighting θ2. θ2 is actually my friend. They are in the same direction, they are your friends. But they get subtracted from each other. That's very weird. So you don't subtract friends. So that's going to be Ts. And what's the value for Ts? Anybody? Yes, yes.
Theta 2 minus theta
One answer. Any other answer? Theta 1 minus theta 2, theta 1 minus theta 2. Anybody else for theta 2 minus theta 1?
Well, it depends on which one you think is greater than the other. Like, if you assume that theta 1.
No, I did not assume. No, no, no. I did not assume anything. You see, which makes it even more stickier, right? So even though I did not assume that it's theta 1 is greater than theta 2, it is obviously theta 1 minus theta 2 because, well, it's not obvious, it's because I want to rotate this guy by an amount theta 1. But this guy is already rotating by an amount theta 2 in the same sense, so the torque I need to apply is actually lesser than what it was in the previous case, and it has to be theta 1 minus theta 2 because I want to rotate it in the same sense as theta 1. Okay? Let me pose the question in a different manner. Let's consider the situation this way. Same thing. Let's look at end O2. Let's see what happens there. Now can somebody help me, first of all, by telling me what the direction of the torque should be if I focus on end O2? Yes?
Should that be counterclockwise because
The observer is from this side, so I'm still going to be in the same direction as theta 2. Okay? It is clockwise or counterclockwise with respect to somebody, with respect to who? Either a person sitting here or a person sitting there. It's your choice, completely your choice. The thing is, theta 2 is the one that dictates how the direction of the torque on that end of the spring should be, not theta 1. Okay, so this I'm going to call as some TS1, just to make it different. And so I'm going to have an equal and opposite TS1 on this side. What should be the magnitude of TS1?
Theta 2 minus theta 1.
Theta 2 minus theta 1, fantastic. So this leads to the obvious question now, which is correct? Is this correct or is that correct?
Both of them.
Both of them are correct. Why?
It depends on where your observer is at.
Not really. I mean, I could be observing it from some other. Let's say that I'm observing this from Mars. Okay? So the laws of physics don't hold true there. Now, from that sense, which is correct? Is this right or is that right? Or am I even looking at any physics here? I'm not looking at any physics here. Is this right or is that right? I'll come back to you. Yes, yes.
They would both be right, because if you started applying numbers, then it would work itself out based on the signs to be whichever, like, they'd only be different by a sign, right? And that
They would be different by a sign, but they're also different by something else, right? So if I focus on this guy, and if I focus on this guy, what are they different by?
Direction.
They're different by their senses, which means that if I flip this, then it is nothing but this guy with a negative sign. So which means they have to work out. It does not matter which end of the spring you're looking at, it has to be the same thing. Okay, you can look at this end of the spring, you can look at that end of the spring, it makes no difference to anybody. Okay? Once again, long story short, look at any end of the spring, look at the senses of theta 1 and theta 2. If they're in the same sense, then one is aiding the rotation of the other, so that the net torque required at any one end is going to be lesser than if the other end was connected to a wall. Okay? So with that said, I'll complete the problem and then take questions. let's just have a digression. Let's say this was the situation. What do we do now? Here is what we do, okay? I'm going to describe this. Focus on any one end, okay? The direction of the torque, let's say I'm focusing on end O1, the direction of the torque that has to be applied on this end of the spring to twist it by an amount theta 1 has to be in the same sense as theta 1, okay? So that's a given. Some TS2 or something, just to be different from the other ones. Then it has to be equal and opposite to what's going on the other side. So this automatically becomes TS2. But now you see what is going on is that theta 2 and theta 1 are not in the same sense. So theta 2 is not your friend. Which means that to rotate this end of the spring by theta 1, I have to overcome whatever else theta 2 is doing on that. Which means that the torque I have to apply is going to be much larger than if this end was connected to the wall. Which means that here TS2 is going to be does this make sense to everybody? I want to repeat it one more time. Okay? Start off with theta 1 and theta 2. These are the signs that I've chosen for theta 1 and theta 2 because somebody told me, why are you choosing clockwise? Why not choose counterclockwise? Okay, here is your gift. Then I say, okay, focus on any one end of the spring. O1 or O2. Makes no difference. Okay? I focus on O1. I need to twist this end of the spring by that amount. Think of it as a shaft. You have seen twisting on shafts, right? A spring is nothing but a shaft. So I'm trying to twist this end of the spring by an amount theta 1. But I see that the other end of the spring or the other end of the shaft has been twisted in the opposite sense. So I have to first of all overcome that. And on top of that, I have to twist it by the amount of theta 1. Which means that now I'm fighting against theta 2 and I have to provide a larger torque to produce the net rotation of theta 1 on this end. Does this make sense to everybody? Any questions that I can answer? Yes?
So then if you were looking at the other side, it would be the same thing.
Let's look at the other side. This is theta 1. This is theta 2. This is O1. This is O2. Now if I focus on O2, what do I first do? The first thing I do is I draw the direction of the torque to be applied on that end of the spring. That has to follow theta 2. Okay, which means equal and opposite back on this side. This is TS3. I'm still focusing on this side. You see? What should be the magnitude of the torque? I see that theta 1 is counter to theta 2, which means that the amount of torque I need to twist the other end of the spring O2 by is going to have an additional burden because theta 1 is at loggerheads with theta 2. And so I see that, okay, this is the same thing. And you see this is quite beautiful, right? Because even the signs of the torques are the same. The directions of the torques are the same. As opposed to the situation here. Okay, here they were at different directions, but then they were also different by a negative sign, so everything worked out here. Here there is not much thought required at all. Everything anyway works out. Does this make sense to everybody? It's very critical that we understand this. If you do this, the dampers just follow suit. You don't need to do any calculations. Just do a theta 1 dot and a theta 2 dot. That's it. Same idea. Last chance for questions. Yes?
You look at torsional springs, do they offer the restoring force in the opposite direction of motion? Like, are they always opposite of theta?
Not opposite of theta, they are opposite to the net displacement of the spring. You see, so here the net displacement is theta 1 plus theta 2. So if there was a mass attached here, the torque on the mass would be opposite to TS2. So that would be the restoring torque. But if there was a mass attached here, the torque on the mass would be opposite to TS2 in the other direction. That is the restoring torque on that mass, which we are going to draw anyways. Okay, so all right. Your last two homework problems for homework 4 are very similar to these, what we have done today, so you can get started on them too. Don't need to wait until Monday. All right. We come back to our problem, okay? Thank you. We come back to our problem, we complete it. So I start off by drawing the free body diagram of the spring and then the damping element. Same thing, you don't need to repeat it. Theta 1 dot, theta 2 dot, TD, T. And TS is AT, theta 1 minus theta 2, CT. If you get the spring, the damper is done. Okay? No thinking required, it's exactly the same thing, same idea. Then I draw the two inertial elements. One here, the other here. This is O1, O2, O1, O2. On the spring, yes, question.
Why is your TD going in the same direction as the angular velocity?
Oh, thank you. That's not still. Thanks. That's O2, not theta 2. This is O2. All right. Then I look at the inertial element here. So this is point O1. This is point O1. This is point O1. And as I mentioned, this is the net torque on the spring. The net torque is a consequence of the net angular displacement of the spring. And so, on O1, I'm going to have an equal and opposite torque to this one. This is the restoring torque on the mass element J1. Okay? As you asked. The restoring torque on mass element J2 is going to be equal and opposite to that guy. That's there. Okay? So here I'm going to have TS, and likewise TD, T1, and then all the other things here. This is TD, TS, T2. Okay? So these are the free body diagrams. I'm just going to draw them out in a much simpler fashion here. Free body and kinetic diagrams. And I'll briefly, after this, discuss a scenario where there could be static deflection of the springs. Right? So if I draw the free body diagram for mass J1 and kinetic diagram, okay, on the free body diagram, I'm going to have TS, TD, and T1. Kinetic diagram, J1, theta 1 double dot, this is O1, this is O1. Is everybody able to understand my figure, my free body and kinetic diagram? All I'm doing is just taking the figures and squishing them into two-dimensional planar figures. Okay, just take this and squish it and then rotate it towards you. Okay. If I then sum moments about O1 on the free body diagram, is moment about O1 on the kinetic diagram. Clockwise, positive because I said so. Tomorrow I'll say counterclockwise is positive. It should not surprise anybody. Okay? It is something that I just choose. It's a sign convention, it's not physics. Then I have T1 minus Ts minus Td is equal to J1 theta 1 double dot. Let me just do this. So T1 and J1 theta 1 double dot. I bring the Ts and the Td onto the other side. So this is plus Td plus Ts is equal to T1. Substitute for Td and Ts, so I have J1 theta 1 double dot, Ct theta 1 dot, Kt theta 1, Ct theta 2 dot, theta 2 is T1. This is the equation of motion for the first mass. For the second mass, I'm not going to solve it. It's straightforward. I'll be posting it in my notes. This is motion for J2. Is going to be J2 theta 2 double dot, Ct theta 2 dot. Check it out and see. Kt theta 2. Couple of things. The positive directions for theta 1 and theta 2 were not motivated by the direction of the applied torque. Okay? The direction of the applied torque could be anything. T1 could be in any direction, either clockwise or counterclockwise. My sign convention is not based on that. If T1 were applied in a direction opposite to the positive sign convention, what would happen is that this would now be counterclockwise and that would end up having a negative sign there. Once again, if T1 were applied in the counterclockwise sense, what would that be having an effect on is, if I come to this equation of motion, this should end up being a negative T1. That would end up being a negative T1, which tells me that the torque is applied in the opposite sense of the positive convention. The sign convention is not wedded to the applied torque, nor is it wedded to the applied forces. The applied forces and torques are functions of time. They can do whatever the hell they want over time. My sign convention is giving me just a guidance for solving problems. It is not telling me this is how the problem moves. Am I making sense to everybody? Is this point taken clearly? Don't be surprised if in your equations of motion in your exam or in your homework, you end up with a negative T1. That's because this fellow would have been drawn opposite to the direction of the positive sign convention. That's all it indicates. Okay? And one more thing I want to do before we take off. Bring the other panel down. Just a precursor to the problem that we will solve next class. Okay? So here is an example of a system where SCP could have more elaborate calculations. So for example,